So we left our story with Galileo Galilei, and we're going to start it again with Newton. 1642, death of Galileo, birth of Isaac Newton. Now some people would say that Galileo Galilei was reborn in Isaac Newton. Not necessarily, but the idea is that, and some scholars, some people who actually have studied the history of science are saying that had Galileo Galilei talked deeper with Kepler, had a much stronger relationship, they might actually have beaten Isaac Newton to his laws. Now that's just ifs. It remains to be that he basically created the basics, the first complete theory of physics that explained a lot of things. So, and the most important thing is that he resolved the question of the motion, of the cause of the motion of planets. So we had a description of planets. We had, with Kepler's laws, we had a description of the orbits. But we know why these things are happening. Now you're going to say, well, wait a minute, how does that relate to heliocentrism? Now we're going to see that the minute you have something that is completely unrelated to geocentrism and heliocentrism, something that is a universal law, and that suddenly explains the description of planets we have in Kepler's laws, explains everything you see in the universe, and is able to make predictions on a range of phenomena that is even beyond the finite realm of the orbit of planets, but are still related to planets, such as tides, then, I mean, you can't anymore talk about geocentrism. Now it's beyond just the description of, well, it's the Earth that is moving or the sun that is moving to explain what we see. We're actually going more fundamental. And by the way, he invented calculus. So if you had trouble with calculus at some point in your life, blame Newton. Now some would blame Leibniz. It was supposedly invented by both independently. But Isaac actually invented calculus because he needed it to basically be able to calculate the orbit of planets from his laws. And obviously he's considered one of the greatest scientists of all times. Guess which one is the other one? Okay, now he came up with 3 laws. The first one is saying that you'll keep going at constant speed on a straight line if nothing exerts a force on you, on the object. That's exactly why you have a seat belt. Because if you didn't have a seat belt, the minute the car hits the tree, it's the car that stops, but there is no force on you, so you keep flying, and you fly out of the windshield. So the minute you're going to stop is when you're going to hit the windshield. That's not what we want, so we put the seat belt. So you're going to keep moving at constant speed on a straight line until the seat belt and the airbag hold you back, exert the force on you to stop you. So that's the reason why we've created seat belts, and because of Newton's first law. But that has much deeper consequences we're going to see. The second law is, okay, now if something could continue forever at constant speed on a straight line, then if I want to change the direction of that object, I need to push on it, then exert the force on it. Now push on it, put a magnet, whatever. I mean, I need to exert the force on it. If I want to, if the elephant is at rest and I need to move it, I need to push on it. But then obviously the kind of force you need to exert on the elephant or on the fly to produce the same outcome are obviously different. So he ended up saying, well, yeah, I mean, the force depends on the mass times the acceleration. Now that means that if I need to change the speed, so either accelerate it or decelerate it, I need to exert the force on it. Or if I change its direction, I need to exert the force on it. Keep that in mind. Change the direction, I need to exert the force on it. Now, his third law is what people call the action-reaction law, but it's essentially the fact that why rockets fly. That's a water rocket, actually. Okay, I mean, it's multi-stage water rocket, but still water rocket. The water under pressure is pushed in one direction, the rocket flies in the other direction. So basically, the pressure in the bottles of water exerts a force on the water in that direction, and then the water is going to exert the force on the rocket in the opposite direction, and the water is going to fly in one direction, and the rocket is going to fly in the other. That's exactly how rockets fly. The third law. And the fact that a force exerts an acceleration and changes the speed. So initially it's at rest, and as the forces continue to exert, the rocket will continue to accelerate. Okay, now the importance, as I said, is that it unified a number of phenomena. One of them is the fact that the apple falling from the tree is exactly like the moon. Now the apple is like the moon. The falling of the apple from the tree is like the moon orbiting around the earth. Now it looks like, wait a minute. So the story behind the apple is related to that concept, to the fact that these are the same thing. So free fall and orbit are one and the same. Now, the laws of Newton are actually used a lot in everyday life. Your car, rockets, interplanetary travel to calculate the orbits around the sun or around objects like that, unless we're dealing with hugely massive and dense objects like black holes and we're very close to them. That's another issue. We're going to get to that. So what's gravity? The whole idea is that if an object moves alone at constant speed on a straight line, if I wanted to make it turn around an object, I need to pull on it, but towards that object. Not actually hold it and move it around. So the only thing I need to do, if an object is already flying in a certain direction, is hold the rope and pull it inward. And so the consequence of Newton's laws was to think that what's actually making objects move in the solar system for planets and the moon around the Earth is a force that's pulling objects together. And that's how he came up with his idea of gravity. And because of the action-reaction law and because of everything, he came up with that expression for the gravitational force. The farther the objects are, the more the force decreases. Now he got that from the moon's motion and from others' motion. So the guy was smart enough to be able to calculate those kind of things and to get them from what he used to observe. Once he understood the principle, he came up with those expressions and the fact that it was related to the mass of the objects. So actually, this is a way to actually measure the mass of the Earth. You just need to calculate free fall. So you let an apple fall, and then gives you that gives you the mass of the Earth. Now, I'm not going to tell you how, neither am I going to ask you to do that in an assignment, but that's essentially it. So the motion of the moon is actually related to the mass of the Earth. And that's how we calculate the mass of planets today. Now, again, when we say it changes like the radius squared, in other words, when I increase the distance, when I double the distance, I reduce the force by 1/4. And so as I move away from the sun, the force decreases tremendously. And you're going to say, what proves that to us that this is correct? Well, let's first look at how these unifies free fall and orbit. Well, think of yourself as actually throwing a stone or a bullet. Now, obviously, the stone or the bullet at some point is going to fall down exactly like this. Now, if I increase the velocity, it's going to fall down farther away because it's being pulled by the Earth down. Now, down is actually towards the center because gravity pulls things towards the center. If the speed is high enough, now imagine it in the following way. The bullet is trying to fall on the Earth, but the Earth is curved. So as it's trying to fall on the Earth, the curvature of the Earth is making it never falling on Earth. And you end up with the moon that is actually falling on Earth, but never being able to hit the Earth. And then orbits are exactly that. So orbits are just due to gravity. Now you're going to say, well, okay, but then how do we know that that expression is correct? Because with his expressions and his laws, Newton was able to reproduce Kepler's laws with a twist. The first one is the fact that because a planet exerts a force on the sun, well, the sun also, because the sun exerts a force on the planet also exerts a force on the sun. So both are moving. But then the sun is so much more massive than the planet that you're barely able to move the sun, whereas the planet is able to move a lot. And then what's basically at the focus is not exactly the sun, it's actually the center of mass of the two objects. The center of mass, if you'd like to think of the pen when you hold it in equilibrium, that's the center of mass. If you put a big mass on one side, you need to move your finger towards the big mass on the other side of the pen. And that's exactly the same kind of concept. So if you have two objects of equal masses, they will both orbit around each other, and the common focus is going to be the center of mass. And we do observe these motions. We do see the sun rotating. I think that Mark asked me that question on the discussion board. Now, the other thing, again, mass of the sun is much larger than the Earth, so the center of mass is closer to the sun. The second one is he did find out again Kepler's third law. So he did explain all of Kepler's laws, the first, second, and the third. But then the more interesting aspect also, now we can easily explain one, because if we say that the period is in years and A in astronomical units, so it's 1 and 1, and the mass of the sun is in one solar mass, then C is equal to 1. And that's why we came up with 1. But then if we express things in different ways, we have to calculate the constants and get the masses. But the idea is that these laws do not apply only to the sun and the planets, but also to planets and moons orbiting around them. And that's now universal. And we've actually used it to find the mass of Jupiter, to find the mass of Mercury, Venus, Mars, the Earth is easily can be calculated just from the orbit of the moon. Everything can be calculated, the masses could be calculated using Kepler's third law. And Kepler's third law is now the balance of astronomers. Now, Newton was modifying. Now you might say, okay, so we push Newton aside. No, the gravity of Newton is not pushed aside. Perseverance, hope, and Misbar al-Amal, basically, and Tianwen-1 went to Mars on an orbit that was calculated using Newton's laws. We didn't need to get the complex mechanics of Einstein. So Einstein, famous, after all, we know it from his most famous equation, E equals mc squared, that's found everywhere, including on t-shirts, on towels, on anything. That's probably the most famous formula of Earth. It's so popular, you find it everywhere. But then the most important part I want you to remember about Einstein is the fact that Einstein modified gravity. He explained it in a completely different perspective. He said, wait a minute, it's not a force between two objects. It's just that a mass curves space-time, bends space-time, distorts space-time. And when another mass passes by, it's going to follow that distortion. So mass changes space-time, curves it, bends it, and space-time is going to tell another mass how to move. Put simply. Now, the best way to explain it is through an actual demonstration, and that's done in the video. So I'm going to invite you to watch it. And now we've understood gravity, and we've reached the end of that historical survey of how we came from geocentrism to heliocentrism.